Hello everyone, my name is Steve Tilley. I'm the Associate Director for the Master of Engineering Management Program at Northwestern University, and we host quarterly webinars and presentations to our students. And tonight I'd like to welcome Dan Heck, and I'll read a little bit about Dan Heck to introduce him. Dan obtained a mechanical engineering degree from the University of Illinois and subsequently worked in the aerospace industry where he developed products for the commercial, military, space, and business aircraft markets. Dan fell in love with training and development while working for Honeywell, and after 15 years, ventured out on his own, building a career by teaching others at large and small firms in the US and 15 other countries. Dan's connection with TRIZ, today's topic, began in the mid-90s when Motorola collaborated with PhDs who specialized in TRIZ and were sharing their knowledge with leading companies such as IBM, Procter & Gamble, and Motorola. So thank you for attending today, and I'm going to pass it on to Dan.
Great. And you can immediately ask the people online, hello everybody, if they've had experience with TRIZ.
Okay.
Or TRIZ.
And is it TRIZ?
Well, I always grew up with saying TRIZ at Motorola, but most people say TRIZ because it's a Russian acronym. So I'm trying to change to TRIZ or TRIZ. But if you say, do you know TRIZ, you would say, yes, I know what a tree is. Who are you, buddy? Well, welcome. And how many of you have been exposed to TRIZ in any form? Oh, good. All right. Well, it is a fascinating subject, and I'm glad you're here because everybody, I believe, every engineer should be exposed to this concept. You are exposed to a lot of creativity and innovation concepts, and this certainly should be in the toolbox that you're exposed to. It's an acronym for this inventive problem solving. It's been validated over 60 years, and it's been in the US for about 20 years. When the PhDs came over after the Cold War ended, and it has been validated in a variety of companies. The point of this, and I'll mention Altschuler's name many times, because Heinrich was this young 30-year-old engineer who this all popped into his mind after World War II. The whole premise is that inventive problem solving is way beyond brainstorming. It's way beyond guess and check. And he journeyed for his entire life until he died in the early 2000s to find out what the science of creativity was, which is very presumptuous to think there's a science of creativity. I've got a bunch of books here if you'd like to peruse them, and there is a variety of texts out there. One of them that I recommend on the last sheet of the slides. Are they going to get the slides?
They will.
Okay, well, I've got a hyperlink to one of them from Ellen Daum and a couple other guys. It's the latest edition that just came out this year, actually. But they're all over the maps, very complicated ones, very simplified ones, and they pick various aspects of the TRIZ theory to develop and unpack. And the problem, I think, is that when you have such a new concept like this and you have technical ways of solving inventive problems, it's almost a mismatch. And it doesn't have the wow factor. It's more of an engineering text, and yet it needs that component of abduction, of wonder, of inventiveness that goes along with these systematic journeys.
So you said 1946 is when...
That's when Altschuler started. After World War, I've got some stuff here, I think. Oh no, after World War II, he was tasked by the Soviets to go and look at all of the commercial inventions, they called them certificates of authorship back then, and see what could be commercialized. What could we use in the commercial world? And he's going through these thousands of them. He goes, there's patterns here. There's some patterns here. And that's when he decided to codify what he saw. And that's what we'll go through. So that was the kind of breakthrough. A lot of people are exploring it and using it. And there's case studies after case studies in the TRIZ journal. So this has been active. Ellen Daum and other people have been doing that TRIZ journal for 20 years. And all of the studies, there's maybe 2 or 3 months, are there. And they have conferences as well. So a lot of material out there to explore. I'm going to cover 5 topics of TRIZ theory that I hope sort of breaks you into the whole game. There's a number of others, but this is the kind of the popular ones, the ones that I've mostly embedded in my own thinking, and it does change your thinking. Psychological inertia, contradictions, abstract the space of interest. Some of these might be familiar to you, and some of you do these things naturally. That's another thing that Altshuler found was that, that's what inventors do. This is what inventors do. And other engineers and scientists just don't think this way. So that's what he codified, and using existing resources. Psychological inertia. So we build things, and as engineering, as a technical community, we love to build on top of what we know. And so we make sense of new material by contextualizing it with what we know, right? That's how we bring it in. And that all works fine, and we grow. Math is a great example of that. We grow things, and they all make sense until they don't. And something comes into the fray that's a paradigm shift. And some of you just get stuck. And others of you then start to sort of swallow hard and allow what you know to work its way into this new paradigm or this new piece of information or this new theory. And that's a very difficult thing for many, many people to do. And that's why good inventions aren't found very easily, because this rearranging of what you know is very, very tough. And Edward de Bono had a great thought about that. Even though, and the idea here is that you weren't wrong. You were never wrong. You just didn't have the same pieces of information you have now. So you don't ding yourself because it didn't fit before. The challenge is, how do you embrace this new information and recontextualize what you know? How do you let your own mind disrupt what you know in order to embrace these new concepts? So that's the first challenge. Be willing to rearrange what you know. Riddles are a great example of that. Here's a riddle. Bob, a 15-year-old boy with a record of violent crimes, approached a screen porch. Taking out a switchblade, he cut through every screen panel with large diagonal rifts. A police officer drove by in a patrol car, saw what the boy was doing, and was pleased. Explain. Anybody want to take a shot at that riddle? So the first thing you know is that it's a riddle. And you probably know that the answer isn't what you would expect it to be, right? So already your mind is somewhat open to thinking, well, it's a riddle. But even though you're giving your brain a little permission to be open, you are just rocked solid to these concepts that Bob's an idiot, he's bad, and why in the world wouldn't the police go and arrest him, right? I mean, it's there, and it's obstructing your ability to explore other possibilities, like a hurricane emergency had been declared and the policeman knew the owner had asked Bob to eliminate wind resistance on the screen porch. Okay. So now you know Bob's a nice guy. Even so, we find Bob in a new situation. Later, Bob picked up a tire wrench and smashed the taillights of a car that he had never seen before. Police officers witnessed his act and arrested him, not him, but the owner of the car. Explain.
There was a baby inside the car.
Pardon?
There was a baby inside the car.
Good. Something, yeah. So he did a good act. He got a tire wrench on. We don't know where he got the tire wrench from. But that would be an example of a good one. And in this case, Bob had been kidnapped, locked in the car, and he had to punch it out in order to wave to the policeman. So that's the idea, is to break the psychological inertia of your mind, because what you think you see isn't the whole picture. And inventors just either park on it longer or see deeper than you and I do oftentimes. And this is a terrific example of where we get caught up in the riddle. This is one of the fundamental theories of Altshuler's TRIZ theory. Leonardo da Vinci did this. Jim Collins, have you studied Jim Collins at all? Leadership? In one of his books, Built to Last, he talked about this whole theory of contradiction and how important it is. Here's the idea. When you have in a situation and you've got these two variables and you want to improve one, the other one goes south. And so you're stuck, right? I want to do this better. But when I do, this one gets worse. That's what we call a contradiction. Unfortunately, what we do, what we've learned to do over and over and over again, what we hear constantly, is in this example. So here's an example one. People want to use their phones inside big buildings to constantly stay in touch. But the signal strength drops. So we could increase power, but the problem there is a shorter battery life. So what's the first thing we do?
Increase the battery, bigger battery.
Bigger battery. And what happens when we do a bigger battery?
Bigger phone.
Bigger phone, so that's no good. So what's the engineering methodology here? We optimize, we do trade-offs, we try to figure out how we juggle all these variables. Okay? Because our mind says you just can't have both things, Bubba. You've got to have one or the other, so let's optimize the variables that we have. So for this situation, we'll identify power levels, we'll characterize the battery life, identify battery life versus battery size, explore phone size variation possibilities, and then do a design of experiments. And we'll be very proud of the fact that with these given conditions, this is the optimum power and battery life we can expect. Sorry. He saw over and over and over again that this was not where inventive minds start. And again, this could be engineers or scientists. Some of them did this, some of them didn't. Some of them were trade-off mentality. But the inventive mind doesn't optimize first. Very important concept. The inventive mind says, how can I have both? I want both. I want both things to be true. James Collins, in his leadership book, Built to Last, said he could notice companies who, with the concept of the tyranny of the ore versus the power of the and. I can't remember the word, the adjective there. He saw companies like the Motorola's of the world that did both. I want quality and I want scale. And they couldn't get all of it, but they were so much farther ahead than the companies who followed the mediocrity of the tyranny of the ore. You want quality or you want schedule. You can't have both. And they would just completely not challenge their brain to try to figure out how to do both. So the inventive mind tries to do both. And because of that, we've got some breakthrough inventions, because there were people there persistent enough to say, how do we get both? Okay. While he went through these, and he went through over 2 million patents back in the 40s and 50s. Some of them were Russian, he went international as well. He found some really terrific, unbelievable breakthrough type inventions like laser light. That's one thing. He found the majority of the inventions were incremental. Didn't take a lot of inventive breakthrough, but they were enough new and enough useful that they could get a patent. But then he saw this 400,000 that were what you would look at it and go, I wish I'd thought of that. Oh, that's clever. So it's got this almost like an answer to a riddle type of response. And that was a very substantial amount, but they were different than the other inventions. So this kind of solidified the fact that these people were solving contradictions. That's what makes these 400,000 colorful, with high fidelity in their inventiveness, is that they resolve contradictions. Okay? And of course, you could say that they are apparent contradictions because obviously they have a solution out there. So that's why we block ourselves by saying it's a contradiction in the first place, where an inventor just says, I want both, and I can't see both right now. So that's a very, very powerful creative space for you to be challenged to generate that contradictory problem statement, or generate that contradictory leadership strategy, and go for it. And obviously, you can go right to Dilbert, right? You can do it to where it's totally impossible, but you can not do it at all and get mediocrity. So you've got to find that sweet spot. Here's a few. For example, how might a pen How might we make a pen that never runs out of ink? How might we design comfortable footwear that is minimal like a sandal and protects the feet from cold and water? Well, that seems impossible. How might we design a process for people to meet everyone at a seminar and look very professional in so doing instead of just giant chaotic mess? So how can we get something that looks really professional, but when you're done, you've got everybody's name and address and some information on them. So how can we crack that nut? Anybody have an example of, online as well, an example of a contradictory problem that they may be dealing with right now? They don't come easy. Nobody online either, huh? They're quiet, everybody's looking. And it usually takes some manipulation and massaging of the variables to finally come up with the statement, because it isn't natural for us to come up with those statements. So another one. How might online gaming be extremely engaging and easy to put down? Once he got that aha and validated it with his 400,000 patents, he made another interesting inquiry. Is there a set of generalized solutions to these contradictions? So you look at all these 400,000 great sort of breakthrough inventions, and you ask the question, can we boil it down so that we have some sort of a methodology here? And the answer was yes. And he came up with these things called the 40 inventive principles. And you can thumb through them, but down, got copies of them down here if you want after done. The 40 inventive principles are the answers in the back of the book type of thing. They are very fundamental. There's nothing really dramatic about them, except we just don't necessarily apply them like we should when we're looking for answers to inventive problems. You can almost guess what some of them are by the titles of them here. And the interesting thing is that whenever we tried to make a set of these for Motorola University, and we would make some, and they would be for the electrical engineers. And the mechanical engineers say, these examples are horrible. I don't understand what you're talking about. What's this definition? Because everybody's got different language, which is a real problem. And then the software guy said, what about the software? I don't see how this fits in the software world. So in a sense, you almost have to take these fundamentals and put them in the language of your discipline to have them be a little bit more helpful for you. But let's play around with this. Let's go back to the problem here. Creating a device that receives signals in all buildings and has the same or longer battery life. One way to use these 40 inventive principles is to just go through them like a deck of cards. Just use them as triggers, so kind of like brainstorming triggers. If these are the 40 fundamental ways people resolve contradictions. Does this one work? No. Does this one work? No. Does this one? So go through those. And in this example, we came up with 4 of them. Number 6, multifunctionality. Well, that might have some possibilities if we think multifunctional. Copying. Can we copy something over and over again? That might have some possibilities. Intermediary. Do something in between the two parts of the contradiction, or periodic action. So you go through those and you think, those got some possibilities. Pull those out, do some brainstorming on those, and you come up with these possibilities. And some of those might work, right? So it's a way to go into generalized solutions that other people have used for contradictory problem statements. It's a great, great tool, I think. So summarize, recognize a contradiction. That's not easy. That's a riddle almost in and of itself, is to create a contradictory problem statement. Recognize that. Go through the inventive principles to see if anything looks halfway close. Select a few of them and brainstorm solutions. That's one very, very simple process that a lot of people do. It's probably the simplest process to use for the 40 inventive principles. Another aspect of the 40 inventive principles is to keep each principle into a query, a question. So inventive principle number 1 is segmentation. So why don't you pass these out? And here's a question bank, which I guess will also be available to those online. And worded in ways that might help you decide whether or not you might think that particular inventive principle might help. So we talked about inventive principle number 19, periodic action. So there's 3 questions here that you might consider. Instead of continuous action, how might periodic or pulsating actions be used? If an action is already periodic, how might the periodic magnitude or frequency be changed? How might pauses between impulses be used to perform a different action? Great questions. Really, really good questions. So this question bank is a really helpful trigger to get a team or to get you as an individual to think more inventively, to think outside so that you can solve riddles. The deeper TRIZ theory goes into a very sort of a math type of model where you take the specific problem and you generalize it. Because your specific problem is in context of all kinds of history and psychological inertia and language that prevents you from seeing anything, that prevents you from seeing, possibly preventing you from seeing something that's new and fresh and useful. So you take your problem, you abstractize it into a typical problem, and you're looking for a contradiction. But there's also, in the middle there, as you see, Altshuler's matrix. He has 76 solutions. He's got algorithms up the yin-yang to really go into these things very, very deep. So he really unpacks inventions, utility, function, and has ways of almost methodically going through that. Some people use that for the really, really tough problems. They sit down and they go roll up their sleeves when the easy answers don't come out, and they start going through these things with some really strong discipline. And they do it again and again because it does show results. So the Procter & Gamble's and Ford's have come up with some pretty powerful stuff. So you do a typical contradiction, you look at the matrix and other ways to look at that contradiction, you find some solutions, and then you put it back into your domain. One of the interesting things that Altshuler or Savransky did in this book, this is 25 years old, on the science of creativity, was to demonstrate that, or he makes the proposition that 96% of the problems you solve have already been solved, folks. Not necessarily in your domain. So you're sitting next to a software engineer or a chemical engineer or an artist or a cook, and they have the solution you need. But there's no way on this earth that you can explain to them in their language what it is that you need, and that is a real challenge. So there's a lot of interesting solutions out there if we could just interpret what we want into the language of what other people want, and that's what this is partially trying to do. Anybody here functional analysis? Functional analysis. While Altshuler was in Moscow, scratching his head at 30 years old after World War II, trying to figure out what the patterns were here, during World War II, at GE, there was a logistics supervisor, and they were increasingly out of material. They had to build stuff, and the stuff was available. There was no steel, there was no aluminum, all these things were getting rarer and rarer, and they were trying to keep up with their supplies for the war effort. And he recognized that if he stepped back and said, okay, that part that engineer designed is made out of steel. It doesn't need steel. Is there anything else besides steel? What is it for? Why does it need steel? Could it be in plastic? And he started to ask the alternative materials questions that drew out this whole discipline of thinking functionally. And by thinking functionally, what do you need this thing to do? You try to avoid all kinds of local language and just understand, got two components here and one of them affects the other. One's a tool, one's the recipient of the tool you're trying to affect. What do you want that tool to do to the object? So we get hung up on like a hammer and a nail, right? What does a hammer do? Hammers. A hammer hammers. But functionally, what is the hammer doing to the nail?
Drives force.
It's what?
Drives force.
It drives force. What's the effect on the nail?
The nail has
What?
It's pushing it down.
The hammer's pushing the nail. What's happening to the nail?
The nail goes inside.
Yeah, it goes. It moves. Right? It goes into the wood. So is there any other way to make that thing go into the wood?
Screw.
All kinds of things to come up. But when we get stuck on the hammer, hammer's the nail, you know, and you're going to hammer the nail. But the functional problem is how might I move that piece of metal? And of course then you can say, what's the nail for? What does the nail do? What's the purpose of a nail?
Yeah, that's like, I don't have to drill the hole, I just need the hole.
You just need the hole, right? But what's that nail and that hole for? What is it for?
To hang something. To hang something or you to clutch.
Okay, so it holds,
It holds, you to clutch.
Attach.
joins. Okay, so the function, so if you go to the function, all of a sudden your mind can break open and say, is there another way to join those things besides a nail? Is there another way to hang that picture? If I need it to hang, and there's the 3M hooks, you know, there's no nail. So that functional analysis abstracts your conversation to yourself and your team in a way that now you can start to think outside of your language and try to eliminate that barrier. Of course, as soon as you do functions to things, you not only get the useful function that you want, but you get harmful functions as well, right? So harmful things. So you describe those, and this is kind of the language, the math language of Altshuler's TRIZ processes. Is as you start looking at these things functionally, and it is amazing how that frees your brain to understand which are the main functions, which are ancillary functions, which are harmful functions, unnecessary functions that you just brought along for something. And certainly today, when we have to be very careful about how we curate all of our knowledge and curate all of the designs people want, it would be a great thing to prioritize the functions that are necessary. You know, what are the 20% of the functions that do 80% of the work, and what are the other 80% of the functions that maybe we don't have to buy or build or design? And that language can really help an organization focus in on the things they need. Interestingly, my boss's boss at Motorola University, Steve Parmalee, who's now out in Coeur d'Alene, Utah. Anybody been to Coeur d'Alene, Utah? Apparently it's gorgeous.
Idaho.
I'm sorry, Idaho.
That's beautiful.
Beautiful place. Well, he's a senior member of a firm in Chicago. The guy decides to move to Coeur d'Alene, Idaho, because he likes it and he can't afford it, and he's a prolific patent attorney. And he did a nice video for us to show how fantastic the language of Altshuler, the language of TRIZ, meshes, this functional language meshes right into utility patents. Because that's what a claim is. What are you claiming the patent does? And it's a function that you're claiming. And so that's a very nice complementary association between TRIZ and good utility patent language. Oops. I think you've seen these S-curves in some other courses possibly. So the idea here is somebody like Edison is putzing around with his light bulb and nothing works, and he's the only one working on it. And so nothing is happening as far as really moving towards ideality. We'll talk about that. But then something happens to where everything starts to come together enough to where there's commercial viability and things take off. And then it starts to flatten out. Well, what flattens out? What takes off? Well, what I'd like to suggest is that what's taking off is the ideal of that. So a light bulb, what's the ideal light? What is it moving towards? Well, we don't want power. we want brightness, and we want convenience. And so all of those variables are moving towards an ideal light bulb or an ideal source of light. And at some point, as in incandescence, they got to a point where there was another curve over there, and all of a sudden incandescent was gone. And something else took off. And now we're trying to get that ideal lumens by all kinds of other ways that are much more energy efficient and brighter and on and on. So that parameter we're talking about is the parameter of ideality. And inventors dream in that ideality mind space. They're not stuck in incremental thinking, especially when you're thinking about a contradiction. Of course, you can't get a light to burn without burning up. Now. But Edison goes, I don't care about now, I care about later. What can I do now that might be burning a little longer, or a little longer, or a little longer? So lots of us get discouraged and stop because now we can't do it. While the Edisons of the world and the Da Vinci's of the world have this sense of ideality. Well, what do I want to go towards? Where's my end game here that would be really, really helpful and a good contribution? Okay. And so that's what you're challenging. And here, the value analysis here is simply function over cost is what starts to kick things in. When the cost goes down enough and there's good utility out of it, all of a sudden there's a lot of players. Until there's not. Good definition of ideality. Ideal system occupies no space, has no weight, requires no service or maintenance, but still performs the main function with all the benefits and no harmful interactions. Why not? That's what we want. We want all the functionality, and it doesn't require any space. So, what's the ideal screen?
No screen.
No screen.
No screen. Well, how can we do that?
Okay.
Huh?
White wall.
We could just put it on a proper wall. Okay, then we just completely eliminate it, and it gives us the ideal function. And it doesn't limit us. If we have this wall, then there's no constraint as far as the length of it, the size of it, how many screens we project. Now there's got to be some functionality or utility reasons we're still here. Who knows what that is? Just as with the chalkboard, we still have chalkboards, and there's still some desire for this functionality in this format. There's lots of reasons for things to stick around. But identifying that main function is a very, very powerful concept to put in your brain if you're inventing. There's lots of noise that can screw up the riddle. What is the main function you're going after? And try to go after that ideally. No questions from the audience out there in the hinterland? Can you tell how many are there? Is it one,
I cannot right now.
6?
I can only tell at the end.
Okay. Here's another one, and this again, it so convicted me as an engineer. Yes?
Does he talk about how to go towards the main function?
How to go towards the main function? Yes. So using the functional analysis, you do all kinds of analysis to your stuff, and you, through the processes that he recommends, is you say, okay, we've got all this stuff that defines our system, and then you can have a conversation of all that, what's the main one? And so you can move people towards that main function. And it could be a debate, because especially in designs, is the main function taking the cork out of the bottle, or is it the elegance of the corkscrew? That's the main, is it the emotional experience that we're at the main function, or is it getting the cork out of the bottle the main function? And so you would have a conversation and design with one or both of those in mind. Good question. Another one that really convicted me, because problem solving over and over again was adding something to the system. You get to fix something, well, you've got to add something to fix it. You can't just use what you have. And he found inventors in the inventive mind looked around the space, that functional space, and said, how else can I use this? You know, for example, in a hammer, you'd have one hammer that puts the nails in. You get a claw to take it out. You know, is there any? You know, it took a long time before the claw married itself to the hammer, to the other side of the hammer. Seems so obvious, but for a long, long time, they were two separate tools. Until somebody said, why can't we use the other side of the hammer? Ford was an early adopter of TRIZ, and this is a great story from them. They had a new compact car that was a real rough idle because there was a lot of systems on that new car that were drawing power on it. So the normal way to solve that particular problem was not to consider it a riddle, but just to consider it a problem. The way we solve that kind of vibration problem is a lead weight. We add a lead weight that dampens, we know lead weights dampen vibrations. So they used that and began research to reduce the demand of idling engine by all the subsystems. So they said, we're going to put a weight in here, then we're going to try to optimize the other subsystems so they don't draw so much wear and energy out of the engine. The projects, but they recognized really quickly that there's just no way this is going to be able to get a successful solution in time. So now what do we do? TRIZ approach. They went through this very sort of laborious process called ARIZ to identify what was going on and what the conflicts were. And then the system says, what resources do you have at your disposal to address this situation? And it turned out that, well, we could use the weight of the airbags because they're there and they're heavy. And so the weights were already in the car. They just had to manipulate where they were. Turned out they had incredible success without adding any additional weight. So it's really, really clever on your part to, instead of going right after adding something, is to say, what's around here that we could use? And this again, this is very good. This is a great parallel to leadership training because you have existing resources. You're constrained by who works for you. It is amazing to me how many skills are in a typical room that have nothing to do with the title that you have, the label that you have. And if people would just communicate better, you couldn't believe the kind of skill. In this room, you couldn't believe what we could all do because of our background. But we're an engineer, or whatever we are, sort of chops off all kinds of experience and functionality that we bring to the table that could be used much more effectively than we do in corporations today. So, to summarize, be willing to rearrange what you know. Just by making the statement, I'm not looking at this thing, I could be looking at this thing in other ways. So how might I look at this in other ways? Be willing to arrange what you know. Describe contradictions. Become friends. Embrace contradictory problem statements, even though they may leave a bad taste in your mouth. See if you can come up with contradictory problem statements and park on them. I've seen this on artists much better than I have on engineers. The artists can do this very well. Constraints. Strip descriptions of domain language. Give yourself a break and try to open up your mind by using functional language, really general language for what you're describing need to be done by your invention. Think ideally. Don't worry about what you can do right now, but what ideally would this system look like in the future. And try to take advantage of what's already under your ability, resources that you have. And that's a quick, fast introduction to TRIZ. Questions? Comments?
Yeah.
Yes.
One thing that was brought up online here is it seems like this is, and I'm trying to paraphrase, like a very arduous process. And it would take a lot of time, but the life cycle of today's world is very fast and short.
Yes.
And is this really doable, applicable?
Yes, it is. And the issue is, when things are happening so quickly, if you don't give creative thinking time to incubate, then you're not going to get necessarily a creative solution. So the quicker you learn to think in a contradiction. The faster you can create that contradiction will help you get into a space, an uncomfortable space. But I contend, and I fight this all the time in my engineering soul, is give myself some space to be inventive. You're trying to rearrange the world in new and useful ways. You've got to give that some breathing room. And I don't know any other way to do it. In other words, if there was a perfect algorithm for it, then we would have a perfect algorithm for it. But this is actually the space that we're going to be moving into while all of you design augmented reality and artificial intelligence systems to do the work that's algorithmic, that's repetitive. It'll leave us to do this stuff that we have to think about. Because we want to rearrange things. Does anybody think of a product or a service in the last 6 months that you went, oh, that's kind of clever? Anybody exposed to a product or a service that made you kind of wonder?
Yeah, I got one.
Good.
So I'm in the process of, at work, evaluating new steel.
Cool.
We're trying to get higher strength steel, so obviously we don't need as much of it, but we're running into problems where the chemistry is such that we get the higher strength, but we're losing weldability.
Excellent.
So we're trying to talk to the mills and talk to the people that are coming up with these chemistries and whatnot to try to find innovative new solutions.
What's the problem statement?
Well, the problem is, how do you get the high strength and the
And weldability.
weldability?
Yeah, that's a great contradiction.
Right.
How might we get the higher strength and weldability?
And, you know, it's one of those things where if you don't pose the question, the mills don't even,
Of course.
they don't even know to think about it. But now that we've been posing the questions, we're getting the mills coming back saying, oh, well, we went and got in our think tank and thought about it, and here's a way we would propose to do this chemistry, or we're getting more and more mills kind of coming on board with, here's the solution, or here's what we think is a possible solution. The only problem we're running into now is, okay, when are you going to make a sample?
Then you get into reality.
Yeah.
That always fights back against this ideal world that, you know, you don't have time for this ideal world.
Right.
And any solutions early on generally have harmful effects too. So not to be discouraged by those, but then you have to, how do we handle these or eliminate those harmful effects? Great example, thank you. What do you think? It sounds something you could put in your toolbox? Yeah? All right, well, I'm done. If you have any questions, then you can feel free to come look at the books, talk to me, have some more pizza. And I hope that was of value to you. I hope I disrupted your mind a little bit to go explore TRIZ. So go take a look at it.
Thank you, Dan. Thank you. And everyone give Dan a round of applause for his time today. Thank you so much.
You're welcome. You're welcome.